Good day. We are in Physics Class 112. We will bring you to the world of Rotational Kinematics. Every day we meet things that are said moving. Some are going up, some are going down. Some are moving in straight line, some are rotating. How do these things rotate? What's the science behind it? Let's do this.
Good morning, everyone. It's Physics 101.
It's 111.
Okay, 112. Today, we're going to show you an activity. What kind of activity?
A clock activity.
Yes, a clock activity. And this will show you something about rotational kinematics. Okay. Consider 3 points on the minute hand of a clock. Let's say that the point A is colored orange, the point B is colored blue, and the point C is colored brown. The point A is on the farthest side of the minute hand. Crap, this is hard.
Oh yeah.
When the minute hand travels
Cherry love dog.
up to 15 minutes.
Cherry love doctor.
There. That's
Displacement.
the displacement is the color in the paper is the displacement of the one in point A. So let's go to point B. So same minute. See there. As you can see, orange is longer than blue, but they both travel for 15 minutes. Next, point C. There. From here on, we can see something. And Daryl will explain what we can see.
Okay. So let's go. Alright. So based on this experiment, we can probably say that the longer the radius, the greater the angular displacement. Alright, we can probably say that the angular displacement is equal to our linear displacement. Alright. And since our linear displacement is equal to speed times time, which means that, well, let's just say that both or these three lines travel at, for example, 15 minutes at the same time, simultaneously. 15 minutes. So after 15 minutes, they would travel with a different displacement, of course, because it's in the formula. Alright. And then, that's it. We have... speaking of angular displacement, we have many ways on how to find our very own angular displacement. Ta-da! These are angular displacement, and we can find it anything else. We can use rotational kinematics in order to find this angular displacement or whatever it is. So we have 4. Alright, if you're listening to our physics class last year, it was discussed by Ma'am Leia. So we have 4 linear kinematics equation. Alright. So these are the 4 kinematics equation. And we can also, actually, these kinematics equations are just the same. And if we're going to convert it into angular. Okay. We have a linear kinematic equation. We also have a angular kinematic equation. Okay. So before that, we're going to talk about. So these are the linear. We're going to talk about the linear, angular equivalent of these linear values. Okay. For example, this linear displacement is of course equivalent in angular as angular displacement. Linear velocity as angular velocity. Linear acceleration as angular acceleration. Okay. So if we're going to formulate the angular kinematic equation, it's just very identical to the linear kinematics equation. We're just going to substitute these values for this value. Okay. For example, we have there the first kinematic equation, which is distance is equal to initial velocity times time plus the acceleration times time squared over 2. So d is equal to angular displacement. Angular displacement. Just like that. And linear velocity is equal to linear displacement. Initial angular velocity times time. Well, we don't have any difference between angular time and linear time, and there's no such thing like that. Okay, plus angular acceleration times the squared of time over 2. So that's our first angular kinematic equations. You can see that it's pretty much identical to our linear kinematics equation. Okay, for our second, so just substitute it like that. So d is equal to theta, vf is equal to wf squared minus over 2 times angular acceleration. It's just the same. And lastly, for the last two, so these are the next would be this one. Okay, final velocity is equal to initial velocity plus linear acceleration times time. Okay, so if we're going to get its angular equivalent, it is final angular velocity is equal to initial angular velocity plus angular acceleration times time. And last one would be this equation, which is distance, or we can probably say that distance is equal to distance final minus distance initial. Okay, so it is equal to d, then will be angular displacement, final angular displacement minus the final initial angular displacement is equal to the holy crap. Okay. So the initial or final angular velocity plus initial angular velocity times time over 2. And that would be our very own angular kinematic equation. Alright, that's all. Pwede na yun. Ulitin na natin yung activity nila.
This is the actual video. Game. 1, 2, 3, go.
This is the experiment that we're gonna do, the activity. We're gonna put the Mentos here in the hanger, in the vented hanger, and we're gonna spin it to try to balance this.
Balance the Mentos first.
We're gonna balance this first.
Yes.
Then
Perfectly
get out
balanced.
of here. Then
Okay.
we'll do this. We
One.
will spin the hanger.
1, 2, 3, go!
Impossible!
And as you see, it is balancing in the hanger and not falling off.
Okay, okay. Stop carefully.
Stop, stop, stop.